So let us take a mental break here. You can pause my lecture or write whatever you want. You remember, just to make jokes, we talk of Sardarjis and Pathans and so on. We can talk of Bahla, right? We can talk of Scottish people, but we are not making jokes about those people. It is just for fun. You remember Sardarjis from my previous courses. They are mostly in India. You know, lots of movies are also about them. Any person who is Sikh, S-I-K-H, it is a type of a religion and so on, and their last name is Singh, S-I-N-G-H, Singh. So anybody who is a Singh is a Sardarji. And in India they just make jokes about them even in those movies and so on. But otherwise they are very big people also. Their previous Prime Minister for 2 terms was Manmohan Singh, a Sardarji. So the jokes are just jokes. So now this Sardarji had to go to meet some people. So Sardarji and his wife are going in a taxi. They are in the back seat. Now after some time, the wife of the Sardarji whispers to him, right, very whispers, that Sardarji, this taxi driver is very bad. He said, what happened? He said that, you see, many times he looks in the rear view mirror and keeps on looking at me. So I feel very bad. And he keeps on doing this, keeps on doing this. Sardarji became very angry. Oh, look at this taxi driver. So he asked the taxi driver, please stop the car. He said, what? You have to go there? He said, no, stop it. So now he's afraid. He stops the car on the side. Sardarji gets out, opens the taxi driver's door. Can I get out? Now that driver is really very worried that now this Sardarji is a big guy. He will hit me, this, that. Sardarji says, you have been really bad. You were looking in the rear view mirror. I will not allow it. Now you go sit in the back. I will drive the car. Okay, so let's get back to the course. So we were talking about how should we design if we know that there is a crack. To know that, we should know the stress concentration. And I was telling you that the way the stress concentration factor Kt is defined, that this is sigma m upon sigma naught, we can't really find it. So here there is a great equation now. This is again a major jump. You have not done this equation earlier, that based on the properties of the material you know, and based on the crack size, this is new. So you can define a stress concentration. So this is the stress concentration K, Y sigma pi A. The sigma is the applied stress. The sigma is the applied stress, F upon capital A. The A is the crack length if it is an edge crack, or if it is a half crack length if it is somewhere in the middle. Y is a new factor. So now this is big, right? This is a very simple equation. Again, we are not telling you now, we will do it later on, how it is derived. But right now, that the first time you are defining a stress concentration near a crack based on the crack size, right? So this is big, okay? So this is the condition when the crack will grow, okay? This is the condition. Now, therefore, you see there are 3 factors here which I have highlighted. Y is something which you don't know about, so let us forget it. Sigma you know, and A you know. So when will K be more? It will be high if Y is large, if sigma is large, or if A is large, isn't it? So Y we don't know. Therefore, the stress concentration factor K will be large if the applied stress becomes large, or it will be large if the existing crack size is large. It makes a lot of sense scientifically that yes, if we keep on increasing the applied load, at some time things will crack. If we keep on having a material with a very large crack, right, it was a very small crack, it will grow for a very long time. But if it is already very large, it can suddenly break, right? So largest crack or the most stress cracks grow first, and therefore it will break. Therefore, to design against crack, you have 2 approaches. either the maximum flaw size, maximum flaw size dictates the design stress. So your sigma, you see this is the equation now. This is the equation. So your sigma should be less than this Kc divided by y pi a. You see, forget about this part, this is your equation. So if you want to have a design methodology whereby your design is safe, then you say, okay, go and check the crack size. And your design stress should be less than this value. You see, y is equal to Kc upon this, sigma is equal to Kc upon y root pi a, right? So this is your design approach. That if you know the maximum crack size that is already there, then you should know this thing, this Kc, which is the critical stress intensity factor, which must be a material property, and you should know the y. We will show you what y is about the crack. And as long as your applied stress is less than this value, your design is safe. So for different values of a, you see on this is the a max and this is the applied sigma. So if your maximum crack that you detect is here or here or here, then what is the maximum sigma that you can apply? If you are in this region above this graph, then fracture will happen. If you are below this region anywhere, then crack will not happen, right? So this is big, that depending on the maximum crack size that you can find in your part, you can decide based on this value that what is the design load. So even if the crack is there, but if your applied stress is less than this value, your machine is safe, your part is safe. The other part of the same equation, is that you know this value, you know what your design stress is. So what maximum crack should be there, otherwise it will fail. Do you understand now? Here you were saying that some crack is there. What is the maximum stress I can apply? Now you are saying no. Based on my study, I know what is the maximum design stress that can be there in my part. So I want to find out if the crack which I see right now, will it fail or not fail the material. So Kc is some property, y is something, and this is the maximum design stress from your theoretical calculations. So you put these values here, Now if you see, because you have taken a outside, so you have to square the equation, right? Remember, now you have to take a outside, so you square the equation. So it is k squared upon y squared sigma squared, right? K squared, y squared, sigma squared, and 1 upon pi. So this you can find, and if the crack that you see is less than this value, then you are safe. If the crack that you see is more than this value, then remove the part, put a new part in there, right? So I am discussing only one slide for about 10 minutes now, but because this is huge, this is absolutely totally new. Anybody who has not done a fracture mechanics course, even though he is a brilliant mechanical engineer, he has even done his masters and so on, he is in the field for 10 years, but he cannot tell you this page. You see, I keep on repeating, you know a lot of material science, you know a lot of solid mechanics, you know a lot of machine design and so on. But always your design theory is that I will try to find out that whatever is the maximum possible force that can be on my part. Based on that, I will select a material which has a good yield strength and so on, and I will design the thickness and the width and so on, that when I find the stress, my maximum possible force divided by the cross-sectional area of my part, then this stress, if it is less than the yield strength of the material that I have chosen, then I am always safe. This is your design theory. But now we know, as 100% surety, that any material that you make, you take iron ore, you crush it, you take it to your steel mill where you are making steel. You take your aluminum ore, you crush it, you take it to the aluminum factory that you can. You see, in Sohar, there is Valley Steel, VALE, Brazilian company, Valley Steel. There they make a steel. Or you have Sohar Aluminum, where they make aluminum. That is what they do. You get the crushed ore and then you make it. But once you melt it and you remove all the impurities and the material is pure, what do you do it? You have certain molds there, and you pour the molten metal into a round block type of thing, or into a square block, or into a rectangular block. So either you get a cylindrical piece, or you get a square piece, or you get a rectangular piece. So you are already manufacturing, isn't it? And you are applying loads and so forth. And from a very high temperature, it is cooling to room temperature or below. So there is cracking and so on possible. So even in this primary manufacturing of steel or aluminum, some small cracks are always generated. Then once you go to, say, the extrusion plant, here NAPCO, then you take the aluminum from Sohar Aluminum in billets, round billets, and you force it through the die in the extrusion plant. So now there are further forces and so on. There will be more cracks. So because of primary manufacturing and secondary manufacturing, there will always be some cracks in the material. If the quality of processing was very good, these cracks are very small in size, microscopic cracks, right? Micro cracks, but they are there. So if the cracks are now there, the material is not a pure, simple material. So therefore now you have to have one of these design theories, that no, I don't depend on the yield strength or the ultimate strength. I depend on something called the critical stress intensity factor. I depend on something called the critical stress intensity factor. Right now you don't know how you calculate it, but this is a material property now, like yield strength, like ultimate strength. So if you know the critical stress intensity factor of a material, then you can tell that if my design stress, maximum possible design stress is this, then at this crack value I am okay, above this crack value I will fail. Or if I have seen with my eye or with my microscope that this crack size is there in my material, then I can decide what will be the largest design stress beyond which my part will start to fracture, right? So this is a theory based on existing cracks. So this is totally new. All your previous theory in engineering or science is based on assuming that the material is pure. It has no cracks or flaws in it, which is not right. Of course, because of what do you call it, safety factor, right? Because of safety factor, you are always safe. You do all that design and then you have a safety factor of 1.5. So even at 50% higher loads and so on, you are still safe. So your design does not work because that theory was right. Your design worked because by practice people knew that we have to have a safety factor. But now, for the first time, you know that if there is a crack in the material, then how should we design it? There is a design example now, just a design example, that there is an aircraft wing. The material has a critical stress intensity factor which is known, 26 megapascal root mean. This is known now. Now two designs to consider, design A and design B, right? We are just asking you to do that, design A and design B, right? So I'll just take a sip of water. You also take a sip of water, pause my slides, and then we'll start again.